All right, so far we found how to find the derivative of a constant, of power functions, x to some power, and we've also talked about sum and difference, where we can take each one a little different. So the big thing in section 3 is we're going to learn how to take derivatives of things that are multiplied and divided. So if I have two functions, f of x and g of x, multiplied together, let's say that is our function, then how can I take its derivative? So an example of this might be y equals e to the x times cosine x. Because as you see, you have two functions. You have the e to the x and you have the cosine x multiplied together. Now, unfortunately, it's not quite as easy as just taking the derivative of the first and the derivative of the second and multiplying together. It is a little more involved than that. And to do this, we use what's called the product rule. So the product rule says if f and g are differentiable, then we have the rule that the derivative of two functions multiplied together, so if I take the derivative of two things multiplied together, it's the derivative of the first times the second function without its derivative, plus the derivative of the second function times the derivative of the first function. So a lot of times we'll write this f prime g plus g prime f. So we take the derivative of the first function times the second function, plus the derivative of the second function times the first function. Now, in a lot of cases, this could be really, really easy. Other cases, a little more complicated. And sometimes I wouldn't use it at all. Now, it will work on this first example, but I certainly would not do the product rule on this. I would FOIL it and take the derivative the normal way. But we can see that it will give us the same answer. Now, if I were to FOIL this, I get 2x squared plus 9x plus 4. You can check your FOIL on that. So using my regular rules, I know this would be 4x, taking the 2 down, 1 less power, plus 9. That is my derivative, 100% done. But we'll do this one with the product rule just to see if it gives us the same answer. So we have two functions multiplied together. So this first one is f and this second one is g. So to find the derivative of this entire function, the derivative of x plus 4, the derivative of x is just 1. The derivative of 4 goes away. Times the second function, 2x plus 1. And then plus the derivative of the second function. Now the derivative of 2x plus 1 is 2. The derivative of 2x is 2 and 1 goes away. Times the first function, which is x plus 4. So I'm going to claim if we simplify this, we'll get the same answer we did by FOILing and taking the derivative. 2x plus 1, 2x plus 8, 4x plus 9. Now, it would be ridiculous to do the product rule on something this simple when you could just FOIL and then take the derivative using our power rules. But I just wanted to show you this is a pretty nice example to show that the product rule does really work. Okay, let's look at another one. This is actually two functions that have two product rules. So if you look at this, we have x squared sine x, and we have 2e to the x cosine x. Now let's just recall, because we do have some of our special functions. Remember, the derivative of e to the x is e to the x. The derivative of sine x is cosine x. And the derivative of cosine x is negative sine x. Those are all just things to remember. So if I'm looking at the first one, let's just do these separate. So if I'm looking at just x squared and sine x, we'll do that one, and then over here we'll do 2e to the x cosine x, and then we can put them all together. So in this first one, this is my f function, this is my g, as you know, according to this rule, f prime g plus g prime f. I would really write that down over and over and over again. F prime g plus g prime f. So my derivative, dy dx, I'm going to take the derivative of the first. So the derivative of the first function is x squared. So the derivative of 2x times the second function, which is sine x, plus the derivative of the second function, well, that is cosine x. The derivative of sine is cosine, times the first function, which is x squared. Now, just for simplicity, a lot of times I'll put the thing with just an x here. Not that you can't put it here and write it like this, but then it almost sometimes gets confused with that x that's in the cosine. So I a lot of times just put the single things with x there. Because I can switch these in the rule. It's just typically the way we write it. Now if I do the second one, this is my f, this is my g. So the derivative of 2e to the x is 2e to the x, because it stays the same, times g, plus we're going to take the derivative of g, the derivative of cosine is negative sine. So this is going to be negative sine x. And again, you can put the 2e to the x back here, but a lot more common notation is just to put it up there. To always put your trig function last in your thing. So this monstrosity here is my derivative. So I had two product rules in the same problem. So let's look at an example how we can use this as a tangent line problem. So it says find the slope of the tangent line to the curve, and then find the tangent line to the curve at that point. Well, this is going to be, the derivative will be fine, plugging in pi over 4 will be fine to find the slope. The tangent line is going to be a little tricky, because if I think of this point, because remember we did tangent lines, we said this is my x value. To find my y value, I would plug in pi over 4. So f of pi over 4, no calculus, just finding the y coordinate, is going to be pi over 4 times sine of pi over 4. From our unit circle, we know sine of pi over 4 is square root of 2 over 2. So my absolutely gross y value is going to be pi square root of 2 over 8. And when you get these transcendental functions, sine, cosine, tangent, e to the x, mixed with an x or a more, polynomial, easy power function, you get these kind of weird points. So now I have to find the derivative. So f prime of x, now again, this is going to be a product rule because we have an x which is a function and a sine is a function. So this is f, this is g. So we're going to find f prime g plus g prime f. So the derivative of x is just 1 times g. So that's just sine x. You can put 1 times sine x if you want. Plus the derivative of g, the derivative of sine is cosine of x, times f, which is x, but again, I'm going to put that x out front just for simplicity's sake. So there's my derivative. Now, for the tangent line, I will have to plug in pi over 4 into my derivative. So again, it's going to be pretty nasty. Some of them will be nice, some of them will not. So we have sine of pi over 4 plus pi over 4 times cosine of pi over 4. So that's square root of 2 over 2 plus pi over 4. And cosine is also square root of 2 over 2. So my slope of my tangent line is square root of 2 over 2 plus pi square root of 2 over 8. So that is the slope of my tangent line. Now, this is sometimes where instead of trying to find b, which is kind of a pain in the butt, we had that one assignment that talked about point slope, which is y minus y1 equals m minus x1. And this is a legitimate way to do find the equation of a line, where this is our x1, this is our y1, and this is our slope. And the reason this one might be an advantage, because if we have to find b, we'll have to multiply these things together, and it will get pretty gross. So if I do this, I'll get y minus pi radical 2 over 8 equals the slope, which is this horrible looking thing, times x minus x1. So this is my tangent line in point slope. So what you should do is you go ahead and graph x sine x in Desmos, and then you put this awful looking thing with the parentheses just like you see it, and it will be tangent at that point pi over 4. But as you can see, you definitely get some issues when you start looking at some of these tangent lines with the trig functions. Nothing we'd ever see on a test or anything, but just wanted to show you that they do exist. Now, for the derivative of a quotient, two things divided, it is a similar thing. There is a rule, just like the product rule, although it is a little more involved. It is the same as the product rule on top. So you see it's f prime g and g prime f, but instead of being added, they are subtracted. So you have your f prime, I wrote it backwards, but you can switch it. So I have my f prime and my g prime and my f, but they're subtracted. And then it has to be divided by g squared. And in this case, f is the top function and g is the bottom function. So f prime g minus g prime f over g squared. So far we have two really, really important rules. One for products, one for quotients. So let's try to use this rule. We'll start with an easier one, if there is such a thing. The algebra in these, I will not lie to you, gets really, really gross. So if we look at this first function, 2x plus 1 over 4x squared plus 2. So this is f and this is g, top and bottom. And I'm just going to rewrite my rule. F prime g minus g prime f over g squared. So to find y prime, I know the bottom is just going to be g squared. So there's nothing really crazy about that. So 4x squared plus 2 squared. Now the derivative of the top. The derivative of the top function, 1 goes away. The derivative of 2x is just 2 because it's x to the 0 and you take the 1 down. So it's 2 times the bottom, which is 4x squared plus 2. So that's my f prime g part, minus g prime. Now the derivative of the bottom will take the 2 down, so that will become 8x to the first times f, which is 2x minus 1. So this is officially our derivative. We just have to clean it up a little bit. So I can use a little bit of algebra. So I can distribute on the top. So I'll get 8x squared plus 4 minus 16x squared plus 8x all over 4x squared plus 2 squared. And so my derivative, I can add the x squareds together. So I'll get negative 8x squared plus 8x plus 4 all over 4x squared plus 2 squared. So that is my derivative. But you can see quite a bit of simplifying goes along with that. The rule sometimes is not so bad, but when you start involving square roots and other kinds of things with these, they can get pretty nasty for sure. All right, let's look at another one. Look at another one over here. If I can get this out of the way. There we go. So here's our next one. So we have an f and a g. And remember the rule for the quotient is f prime g minus g prime f over g squared. So if we're going to find the derivative here of f of x, so we're going to take the derivative of the top, which is going to be 4x, because I'm taking the 2 down and 1 less power, plus 4, and that's a constant, times g, which is x cubed minus 9. So that's just this portion right here. Minus g prime, so the derivative of the bottom is 3x squared, and then the 9 goes away, times the top, which is 2x squared plus 4x minus 2, all over g squared, which is x cubed minus 9 squared. So again, now we have our derivative, but this has got a lot of simplifying we can do. So we can FOIL the first two. So it's 4x to the fourth plus 4x cubed minus 36x minus 36. And I'm just foiling it in. This times this times this. Here I can distribute. So we get minus 6x to the fourth minus 12x to the third plus 6x squared all over x plus x cubed minus 9 squared. And you notice I'm not really doing anything with the bottom, just leaving it as whatever squared. And that's typically what we do, because what we'll use these for is we are pretty okay if that's factored on the bottom. So I'm not going to mess with it too much. So these are both x to the fourth. So that's minus 2x to the fourth. Here's an x cubed, here's an x cubed. So minus 8x cubed We have 6x squared. We have minus 36x and minus 36 all over x cubed minus 9 squared. So this one becomes really, really bad. We do not like this one very much, but not the end of the world. So now that we have this product and quotient rule, we can actually do some other functions with it. We can actually take the derivatives of our other trig functions. So the derivatives of tan, secant, cotangent, and cosecant are shown here, but I want to prove how we get one of those. So for example, I think I'll prove how we find the derivative of tangent. Why is the derivative of tangent secant squared? It's not really particularly clear why that's true. So let's let y equal tangent of x. But if you recall, the tangent of x is the sine of x divided by the cosine of x. That's one of those pre-calc trig identities we use quite a bit. So what we can do now is this is a quotient, f and g. So I can now use my new product rule or quotient rule that I just learned to find the derivative. So if I find the derivative of this y prime, the derivative of f, the derivative of sine is cosine of x, times g, which is cosine x again, minus, because we got the minus sign, g prime. Well, the derivative of cosine, remember, is minus sine x times f, which is sine x again, all over g squared, which is cosine squared x. Well, this works out really nice because if you look at this, this becomes cosine squared x plus sine squared x over cosine squared x. So one of our big identities we learned in pre-calc was cosine squared plus sine squared was just 1. So this is 1 over cosine squared x, and 1 over cosine is secant. So this is just secant squared x. So there's a really, really simple proof of the derivative of tangent. So this would be a really, really important thing to keep in mind. We have the derivative of sine and cosine and e to the x on the previous page. Now we have tangent, cotangent, cosecant, and cotangent. So these are just things that you keep building up your repertoire for. We have all these different derivative rules. So not a terrible idea to get a big piece of paper, start writing these down so you have them all in one place so you can refer back to them. So now that we have these rules, we can certainly use them. So we can differentiate these. So we have x squared times secant x minus 4e to the x tangent x. Just to make this a little simpler, we'll do it in two things again. So again, we have f and g. So these are products because it's two things multiplied together. So remember, we have the product rule, f prime g minus g prime f. So the derivative of x squared is 2x times g, which is just secant x. So this is all just for this blue part. Plus the derivative of g. So the derivative of secant x, if you look above, the derivative of secant is secant tangent. So the derivative is going to be secant x tangent x times f, which is the original function, which is x squared. So there's my first part. That's my derivative of that blue part. So then minus, if I wanted to do the derivative of the second part, it's going to be minus the whole derivative of this. So it's the derivative of the first, which is 4e to the x, which is still 4e to the x, times tangent x, because the derivative of e to the x is still e to the x, plus the derivative of tangent. So we just proved that the derivative of tangent is secant squared x times f, which is 4e to the x. Now you notice I have this minus sign and I put it in parentheses because that's pretty important. Because our final derivative, if I want to write it out, is 2x secant x plus x squared secant x tangent x. And then I really need to distribute that minus. So minus 4e to the x tangent x minus 4e to the x secant squared x. That is my official derivative. And again, this one was two product rules. So we had a product rule for the first and a product rule for the second. just to get us a lot of practice doing a lot of different functions. In general, I'll probably only put one of them, but just for practice on the notes, I thought this would be a good idea. So the last one we see here is sine x over secant x. So this is a quotient. This is two functions divided, so f and g. So in this case, I'm going to have to do the quotient rule. F prime g minus g prime f over g squared. So if I want to do the derivative of g to the x, so g prime of x, it's going to be the derivative of f and the derivative of sine is, of course, just cosine x times g. Now g is this secant x, so that's secant x. That's interesting. Minus g prime. Now the derivative of secant is secant x tangent x times the first function, which is sine of x. So that's kind of a mess. All over secant x squared. Now, you can try to play around with this. You can try to see what you get. If you got this, I would be pretty happy with it, but it actually does simplify pretty well. So if you simplify it, this becomes cosine x. Secant is 1 over cosine x, if you remember that from pre-calc. Secant x is 1 over cosine x. So now we're just using those trig identities we learned in pre-calc so long ago. So we get this all over secant squared x. And I'm just doing that to see if stuff cancels out. And you can see one thing cancels out. This cosine is on the top and bottom. So this becomes g prime of x equals 1 minus. So we have sine squared on the top and cosine squared on the bottom. All over secant squared x. So I can rewrite this as 1 minus tangent squared x, because remember, tangent is sine over cosine, all over secant squared x. I believe that's as far as I can take it. That top is close to an identity. One of the more obscure identities is 1 plus tan squared is secant squared, but this is 1 minus, so it doesn't work. Again, if you got up here, if you got to this point using the quotient rule, I'm pretty happy with that. But a lot of this trig simplification can help you along the way. Okay, another thing we'll talk about, and this is a little simpler, is we're going to talk about things called higher order derivatives. So we've taken a derivative, and we have all these rules, and there'll be more, so we're not done adding rules. So we have all these rules, and we can find the derivative. Well, we can also find what's called a second derivative, or a third derivative, or a fourth derivative. And what you just do is you just take the derivative of the derivative. So a second derivative is a derivative of the first derivative. And a third derivative is a derivative of the second derivative. And it just goes on and on and on like that. So sometimes when you take a derivative, you have to use the product or the quotient or the power rule. All these things apply. And you can see our notation. For second derivative, instead of y prime, it's y double prime or f double prime. Or for the d notation, we do d2y dx2. So in some of them, like this first one, you can actually find all the higher order derivatives, because what will happen is it'll eventually go away. Because y prime is going to be 8x to the third minus 18x squared plus 8. And then the 9 goes away. Y double prime is just going to be the derivative of that. So we'll take the 3 down and we'll get 24x squared minus 36x, and then the 8 goes away. So you can see each time you're getting rid of terms. Doesn't have to be every time, like in this case I won't get rid of anything, but the powers go down. So this is 48x minus 36. So the fourth derivative is going to be just 48, and then the fifth derivative would just be 0. And now there's no more derivatives, because the sixth derivative would be 0, the seventh derivative would be 0, all the rest of the derivatives would be 0. So in polynomial functions, you always get this kind of thing where all the derivatives go away. That doesn't always happen. Sometimes the derivatives will just continue and get worse and worse and worse and worse. Like this next one you'll see, we're going to try to find the second derivative of secant x. It'll get worse and worse and worse and worse and worse. We're going to just find the second derivative because that will be plenty enough. So we have this rule for secant. So y prime is going to be secant x tangent x. But if you notice, these are two functions multiplied together, secant and tangent. So this is our f and g. So we have to use our product rule, f prime g plus g prime f. Anytime two functions are multiplied together to find their derivative, I'm going to have to use this rule. So y double prime is going to be the derivative of f. So the derivative of secant x is secant x tangent x. That's the rule from the previous page. Times g, which is just tangent x, plus g prime. Now if I look back, the derivative of tangent is secant squared x, times f, which is secant x again. So if I simplify this, I can say it's secant x tangent squared x, because I have two tangents here, plus secant cubed x is y double prime. Now, if I took the derivative of this again, well, honestly, there are rules in here we do not know yet. Like this would use what's called the chain rule. This would just get worse and worse and worse, and it would keep expanding over and over and over again, and it really would never stop, as nice as the previous one did. Now, there is one application we can look at that deals with higher order derivatives, and that's acceleration. Now, acceleration is how velocity is changing. So how fast the velocity of a object is changing. So when you push your gas pedal, you are accelerating, so you are speeding up. You are increasing your velocity, so you have a positive acceleration. When you hit the brake, you have a negative acceleration because you're decreasing your velocity. Now we know that if we have some position function, we'll say s of t, then the velocity, if we recall from the last section, is the first derivative. So v of t is the first derivative with respect to t. Well, acceleration, since it's how velocity is changing, we can say acceleration, and we'll call it a of t, is the second derivative of position, or the first derivative of velocity. So it's how velocity is changing or how the position is changing with respect to itself. So if we have this example here, it says given position of object given by this equation, find the velocity and acceleration after a second. So if I were to graph this, it starts at 32 and it looks something like this. So it's some kind of object like this. So this is my my axis of t, and this is height. So if we think about 1 second, t equals 1. So it's somewhere up here. I don't know exactly where it is. So we want to know how fast is that thing going, and is it accelerating, is it decelerating, things like that. So if we look at the first derivative for velocity, it is the first derivative of our position function. So it's h prime of t, which is negative 32t plus 114. And our acceleration is going to be the second derivative of our position function, which is negative 32. So this is interesting, negative 32 for our acceleration. And we'll go ahead and say this is going to be in feet per second squared. That's typically a pretty typical value for acceleration, some linear unit over second squared. Well, this is actually the pull due to gravity. Negative 32 feet per second is what the gravity pulls at us on Earth. So with this object being launched this way, the only thing really pulling it back and slowing it down is the Earth's gravity. So at time 1, if I were to plug 1 in for this, we still get negative 32 feet per second squared. Now for velocity, velocity will change because it has a variable. So if I want to know the velocity after 1 second, I could just plug in 1 for t, and so I get 114 minus 32, and that will be 82. And again, I'm going to assume this is in feet per second, because it's feet per second. It's how many feet you're moving every second, and acceleration is how many feet per second are you changing every second. So that's why you get the square in the bottom of acceleration. So that's a pretty common application of a second derivative. but there are a ton of other applications out there. Hopefully this is not too bad. Obviously the big things in this section, product and quotient rule. Let me know if you do have any questions over those concepts.